and thanks for being here. It's great to see you all here in Stockholm. So the title of this presentation is How to Scale Up from Servers in Your Apartment. So the backend infrastructure of Spotify started very small in an apartment and then grew to the very large scale that we know today. And I will show you how the design of computer network infrastructure changes radically depending on the size. And I will also guide you to pick a good architecture for your situation, whether it's large or small. I'll start by introducing myself. My name is Leo. Hello. I work for Spotify in Stockholm. And I joined the company 6 years ago. I've been working in backend infrastructure for the last 3. And in this time, I've been working mostly on computer networking infrastructure. So I've been thinking a lot about how to run big things and big infrastructure. But that's only the last 3 years. And before, I worked in something very different that had to do with systems for customer support. And that's very different because those are internal, so they have a small number of users. But they're also complex because customer support needs to handle a very wide range of problems, basically all the problems. In my experience before Spotify, I was working at different consultancies, usually building business software for small companies. And in that case as well, the scale was even smaller. Maybe it was the logistics department of some company, but the business was quite complex. So throughout the years, I've been fascinated at how those systems of different sizes, they are quite different. And it's quite interesting, I find, to compare all of them. So I will show you some of these differences today. So let's start from Spotify as it is today. We all know it's quite large. We have a quite large infrastructure. But to get an idea and to be a bit more specific, let's look at some numbers. And those are numbers you can find at Spotify engineering page. So if you go there, you will find this image. And I will read some of those numbers. You can see that we receive in the bottom left more than 6 million client requests per second. Then moving towards the center of the image, we see that we have more than 2,900 microservices in production. In the middle, we see about us, the engineering organization. We have more than 460 squads. These are teams. And more than 2,100 engineers. And then the last number I am reading that I think is relevant is at the top right. We make more than 1,000 deployments per day, which means that all of this infrastructure is constantly moving. So it's pretty large. But of course, Spotify didn't start this way. Spotify started very small. And according to legend, it started in an apartment of one of the founders. So that's where the servers ran at the beginning. And this is many years before I started at Spotify, so I wasn't there personally, but this represents how I expect that it looked like. It was just a home, maybe a kitchen and a table and some servers on it. It was sometime in the 2000s in an apartment around Stockholm. And it's similar to stories of other companies that started in a garage, except that in the Stockholm area, not so many people have their own garage, so apartment it is. So, as I said, I think it's quite interesting to look at the differences between something very small and something very large, and what are the things that become better when you grow, and what becomes harder or really worse when you become bigger. And I will try to help you to make your own decisions by showing you all that. Okay, so before we dive into a description of what a possible architecture from very small to very large looks like, let's try to see what success looks like, because we need to always use our problem-solving skills and to try to solve something. We need to know what we're trying to do. So let's define what success is like. And the thing you're trying to build depends on the business that you're trying to run. So that but your infrastructure should support the business in a certain way. And we need to define what it means to be successful. So let's say that you want to serve your business and you want to achieve the right cost, scale, availability, and latency. Those are non-obvious, I think, and your needs can change vastly. So I will go quickly in the next couple of minutes into every one of those. I'll start with what I think is the simplest to reason about, which is cost. Because when you start off, you most likely have very little money in your hands. Also, you have very little time, because it's probably a bad idea to spend most of your time building infrastructure when you're starting off. You probably want to spend most of your time thinking about your business. So cost is also a big constraint when you're very large, because of course you have a lot of money at your disposal now. Your budget is now very large, but also as a large organization, you are also expected to be way more diligent in how you spend it. You really need to spend wisely. So cost is always a big concern, but changes a lot how much budget you have. This is the most obvious one, I think. Then the next one that I think is easy to reason about is scale. And you can mean different things by scale, but you can think about, for example, the number of users you have. And even within the same company, in the example I made from my experience, you could work in the whole infrastructure, so think about very large scale and serving all of Spotify users, or you could think of something internal that has many less users, or you could work on many much smaller user bases. And that you only know about. The next one is availability. So availability is a way to describe for how much time your service is working or not. And it's usually measured in a percentage, for example, 99% or 99.99%, which is the time when your service is available compared to when it's not available. And you might be tempted to say that you want to have the best availability possible, that you want to have 100%, but this is basically never the right answer, even within the same business. So if you take, for example, an e-commerce company, an e-commerce business, you will have some systems that make sure that your customers can go to your website and they can see products. They can look through them and they can make a purchase. And if the systems that serve that fail, for every second that that happens, they are going to be frustrated. They are not buying and they're going away. So that's super important. But the same company will also have other systems. They will have inventory system. They will have delivery systems to talk to delivery couriers and internal, I don't know, health, human resources systems and a lot of other important things. But those parts, those systems, they could be unavailable for minutes and even hours, and no one would care. So you really need to think what availability you really need depending on the part of your system that you're talking about. And the fourth quality that I'm showing to you is latency. So latency is a way to measure the time it takes to respond to a request. And here again, like, first, it's usually measured in an aggregated way because it's not very useful to measure a single request. You want to express a number that tells all, like in a single way, all of them. And there are many ways to do that, but you can use some statistical tool like percentiles, and you can usually say you have a P99 of a certain number of milliseconds. But here we can make a similar, you should make an argument similar to the previous one, that there are certain systems that if they are slow, your customers will immediately perceive a sluggish and bad experience. But most likely, many of your systems don't, and it doesn't really matter. It depends on the system, and you need to think about this. Interestingly, how much latency you need depends also on choices you make that are in your control. For example, you might have a mobile app, and depending on how you design your app, you might have a situation where a slow response from the backend can make the app sluggish to use, or the app could be designed differently in a way that all requests to the backend happen in the background and don't directly affect the customer experience. So it could be in your control even, and you really need to think about it. So in the end, what we're trying to do is that we are looking in different sizes of architectures how you can address those challenges as you grow. So let's get started. The first step, maybe a bit surprisingly, is to have only one server. And you have one server, it can be in your apartment or in your office, or it can be in the cloud, and then you would say it's a virtual machine in the cloud if you want. It doesn't really matter, it's still one server. And there is not much to say, it's very simple. It's just a server, right? So you have an apartment, or an office, or a cloud provider, and then you have a server and some data, and that's the simplest backend architecture you can imagine, and that's it. So why would you even do that? It sounds like a terrible idea. Like in this day and age, having a single server, why would you do that? You need at least Kubernetes, right, to be respectable. But, well, there are very concrete and useful advantages in having something extremely simple. Let's look at the good parts. So with a single server. So the first thing that I would like to point out is that if you have a single machine, you basically can design your application any way you want. And that's convenient when you're starting out. You will be coding quickly, you will have to produce some kind of proof of concept very quickly, and you have something that runs in your computer, and it could be anything. And if you have on a single machine, it's most likely you can run the same thing in production. Also regarding deployment, you don't have many problems there. So if you have some advanced automation that allows you to make deployments very safe and automated and fast, it's all good, but you don't really need to be very advanced there. Like, you can basically use anything as a way to deploy code to production. It could be, sure, a container. If you're in the Java ecosystem, it could be a jar. If you are using an interpreted language, it could be just code that you fetch and ship to the server. It doesn't really matter. Anything works, and you don't really need a separate infrastructure to make your deployments work. And also regarding storage, you can choose whatever database works well for you, or even you're familiar with, and most likely you can run it in a single machine. And also regarding routing traffic from your customers, you're just in one place and the traffic is going through the internet, which means that you don't have to configure it and you don't have to pay for it. Whereas internally within cloud providers, some network traffic you have to pay for, and you have to configure and you have to design. And also there is observability. So if you are in any way serious about your infrastructure, you need to look at it. You need to observe if it's working well. You need to see if you have failures. If it's getting slow, if you are overloaded, and if it fails and there are errors and crashes, you need to go and look at the logs. So all of this is called observability. You definitely want that. But if you only have a single machine, there is nothing to aggregate. You just go to the machine and look. So you don't need any supporting infrastructure just for that. Of course, it's pretty good, but it's not all good. There are many bad things. One obvious one is scale. Eventually, you will have more traffic. You might have more traffic than a single machine can handle. But in practice, it's very common that this will not happen. You could have a successful business that doesn't need a lot of scale. A more obvious problem, though, is availability. Because if you have a single thing, and that single thing breaks, like that, now you have a problem. And if it's in your kitchen and it's literally on fire, then it will take hours until you put out the fire, and then you go and order a new one, and then everything like that. But even if you have a virtual machine with a cloud provider, of course you will be much faster to get a new one online, but it will still take some time. And if it's failing a little bit, then you have a problem. Like, you will try to replace it with another one, but you're not in a good position for availability. So again, depending on what you need. So the most obvious next step is not have one server, but have many. So that will be step 2. Let's call it the data center. So staying with the apartment example of before, a data center could be an apartment with many servers, or it could be a cloud provider as well. So in that case, now you have multiple application servers. The application now could be a single application, usually called a monolith, or it could be many services. Some people like to call microservices. It doesn't really matter, but you have more than one. And you need there is a new component. I wrote API server dash load balancer. You can do this in many ways, but you need a way to receive traffic from the outside and send traffic to application servers that work. And you need to realize which one works, which one work and which ones don't. So you need to do that in some way. Then your storage. Storage is a bit more complicated because when you lose an application server, you can just get a new one. But when you lose a database server, you also lose your data. So there is state involved, and state is hard. So if you have 2 database servers, suddenly you have this horizontal line, which is replication. You need to figure out in some way how your favorite database does replication. And most likely it can, but it's not simple, and it depends a lot on one database to the other. And then there are 2 boxes. I'm going very quickly through them without many details, but you need some way to discover which instances you have of an application or a database, some form of service discovery to find out where they are, because they could change quickly. And then you really need a way to do rollouts throughout many machines. You probably want to do them one at a time. You want to make sure that traffic actually is not lost when you're doing this, and so on. So I will do a quick digression to storage, because I mentioned before that it gets more complicated, but I want to give you a specific example to that very quickly. And the example is this. Imagine you are a hotel booking business, and there is only 1 room left. And now you have a customer that tries to book that room. What do you do? Do you want to be sure that no one in the world is trying to book the same room so that it's not double booked? Or do you prioritize being able to serve all of your customers? The answer is that there is no good answer. It depends on your business. You need to make this choice. And there will be situations where your database servers cannot talk to each other. There will be a network partition. And then you have to decide what to do. You need to decide if you accept occasionally double bookings, or so if you want consistency or you want availability. And I want to insist on the fact that with storage, there are many choices, but there is no one good choice. The bigger you get, the more constraints you have and choices. So let's look what's good. Let's look at what's good and what's bad with a data center. So you should be able to be more available by now, because you have any single server can fail, and your load balancer should somehow send traffic to another place. And that's good. You definitely have more scale. If you have success, you should be able to just add more machines, or virtual machines, or whatever it is, or Kubernetes pods. And that should be fine. But there are also problems. As we saw, there are many more components. Things get more complicated. This load balancer that I didn't talk much about can be very complex. As I mentioned also, your storage has many more constraints now. You need to make more decisions. It could be that the database you like doesn't work well in this highly replicated environment. And your app as well, you need to be sure that you can make copies and there is no state there. So the app needs to be well structured. And also, you're still in one place in the world. So if your customers are far away, they could find the experience too slow, depending on what they need. And also, all your servers can still fail all at once. And why? Because they are in the same place. And many things can happen in a single place. Like you can have a blackout. And then maybe you have alternative power, but then your internet connection will fail at this point. Or you could have, probably in your data center, you will have some sort of networking infrastructure or switch or something that connects everything together. And there will be a time at a certain point when someone will go there and they need to do their job and they're trying to add something new, and they will pull the wrong cable and down goes everything. And we might laugh at this and find it a bit outdated, but if you are in a very advanced like cloud architecture, probably cloud provider will give you a virtual version of that, something like a virtual private cloud, so a virtual representation of your private network for your organization. And then you're back here, like you have some configuration somewhere, and there will be a time where it can totally happen that you you, instead of pulling the wrong cable, you will make the wrong configuration, and then all goes down at once. So that can still happen. So what to do? Many data centers, of course. And here I'm using the language that usually cloud providers use. They usually call something like a data center a zone, an availability zone, which is a set of servers and infrastructure that can fail all at once usually because they are using the same power, the same infrastructure. And by region, they mean a whole geographical region, like, for example, Sweden. Now things get more complicated. We have a whole copy of everything we had before, and then we have another load balancer outside. And I wrote DNS. This is just an option. There are many ways to route traffic to different data centers. But you have another layer, and you have another big duplication. And I drew a scary dotted line between the databases, and I'm being very vague here, but you still want to have your data available everywhere. And now you need to make sure that all your databases have the same data. You need to solve that somehow. So how does that go? You know the drill. Availability should get better. You can probably survive zonal failures if there are no regional single points of failure, or maybe your cloud provider sneakily put in one, or you did without realizing. But usually you should be able to survive a zonal failure. And you're still in the same area, in the same region, so you can probably manage to get database transactions and consistency if you need them. It will not be easy though. Storage will be complex. If you have your favorite SQL database and you want to have it work in there, it might work or not, and it might be expensive or not. And also routing, of course, gets complex or expensive or both. You have a lot of choices now because every time you have a microservice speaking to another, you need to decide, do you want to always stay with the same zone and then trust that that zone will always work if all services in the zone will work all the time? Or do you want to have the ability to send traffic from one zone to the other? In that case, you need to be able to make the decision somehow. You need the system to do that. And then you need to pay for that traffic because usually cloud providers charge you from traffic from one zone to another. All of this can totally be solved, but it's complex and it can be expensive. And you're still in one side of the world. So a region, for example, Sweden, is still only Sweden. And if your customers are somewhere else, it will be slow. Why? Because sending traffic over an ocean takes time, and especially containers, but any kind of traffic. So again, we know the drill. If one region is not enough and we want even higher availability and you want to be close to all of our customers, just get 2 or more. So that's step 4. Now we take everything we had before and we duplicate it into regions. In that example, I put Sweden and Brazil. So you have 4 zones, Sweden 1, Sweden 2, Brazil 1, and Brazil 2. And roughly, it looks similar to what we had before, but now we have even more pieces, even more decisions to make, even more levels of load balancing. And for example, for the load balancing, really get complex now. There are similar problems to what I mentioned before. You need to decide if you want to allow or not to go from one zone to another, from one region to another. You need to decide if you want to keep some form of data locality or not, if you want your data from your Swedish customers to be in Sweden or not. Because if you do, then you're not able to route your Swedish traffic, your Swedish customers to Brazil because their data will not be available. But again, all of this can be solved, but it really gets complex now. And synchronization of database transaction throughout a very wide area is something you should not even attempt, because since it takes a lot of time to do a round trip between Sweden and Brazil, if you expect your database to be globally strongly consistent with a very high requirement for consistency, you will have other problems. It will be very slow probably, or very expensive, or both. But yeah, you can totally do that and have many regions. So what's good, now you're close to your customers. You can serve them fast, hopefully. You can actually go very big, because if you really, really have a very large infrastructure, you can do more than, you can tap more infrastructure than what is available in a single region. And that's good if you're very, very large. And if you're lucky, you might even survive regional failures. I mean, global failures do occur in systems, but at least you should be able to survive the regional ones and the zonal ones, hopefully, if you manage to route traffic somewhere else around the globe. But of course, it's very complex. As I mentioned, storage brings very hard choices. It could be that you don't need, you have very small requirements for consistency, and then maybe you're fine, but you have a serious discussion to have about your data, definitely. Routing, as I mentioned, is complex. Okay, so now we went through 4 steps, and we started extremely small, and we ended up extremely large. And I hope to have showed you that they change a lot. So steps are 1 server, 1 data center, many zones in a region, and multiple regions. And what I urge you to do when you design your system is not to necessarily follow advice you see from large companies, because many large companies do what's convenient for them, but what you need could be very different. And to figure out what you need to think in some way about what it is that you need. So you need to think about, for example, what cost, scale, availability, and latency you want to achieve. And it's totally fine if you need something very small. Like in other kind of endeavors, it's quite common to imagine that, I don't know, a neighborhood bakery is very different from a multinational food corporation. And both can be a lot of fun and have different challenges. So you should completely embrace it, even if you're very small. And when you do that, you should always stay as simple as you can, because you can always add complexity and create more problems. But the real fun challenge, I find, is to do things as simple as you can afford by respecting what you actually need. And yes, it's going to be fun. So to summarize what I'm trying to share with you in a single sentence, you shouldn't really try to scale up or scale out. You should scale right. Thank you.